Yo, 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 looking at sections 2, 3, and 2.4, looking at biconditionals, some definitions, as well as some deductive reasoning. So in our first thing, we're looking at a biconditional, and this is where we're taking two true statements, and it's the conditional as well as the converse, and these both have to be true. So looking in terms of looking at these symbols, we have P to Q, so this is if and then statement, then we switch that order, and then if both of those are true, then we can use this. We have a new symbol here which states for if and only if. So if our original conditional, and then we have if and only if our conclusion. So let's look at an example of that. So in this first one here, I have if a number is negative. So we can see here, this is our hypothesis, and then the cube is negative. This is our conclusion. So to write the converse, we just switch the order of those things. Now we have if the cube of a number is negative, then the number is negative. So that means like the original number we started with. So like if we cube -2 times -2 times -2 gives us -8. So we can't prove these wrong with a counterexample, which allows us to write a biconditional. If one of these was false, then our answer would be A. But since they're both true, I keep it in the same order as the original conditional statement, and I replace if and only if. So it's the same order. A number is negative. If and only if the cube is negative. And number 2, we're doing the same thing. So here we're looking, this is our conditional statement. We make the converse, and we have to see, are these both true? And if we look here, we say if the square of a number is positive, then the number is positive. That's not true. I can square -2 and I still get a +4. Since this is false, then I cannot write a biconditional statement. More examples of looking at biconditional statements. Here we're given this, a biconditional statement, and we have to break it down into its conditional as well as its converse. So I see here, this is my hypothesis and conclusion, and then we switch that order. In number 4, we are doing the same thing. We're looking here. This is my hypothesis. Here we go. My conclusion. Here we go. And then I switch the order for the converse. In number 5, here we have to test these, and I wrote them out here to the side. So we're given a statement here, and I wrote them both as a conditional statement and a converse. So if two angles have the same measure, then they are congruent. So this is a symbol for congruent. It's like an equal sign with a tilde on top. And then if two angles are congruent, then they have the same measure. So if both of these are true, therefore I can write a biconditional statement as you see here, and we keep the same order. So if two angles have the same measure, if and only if they are congruent. And number 6, I'm going to follow the same rules. But we see here that this one fails. So if two angles form a linear pair, then they are adjacent. And if you don't know what adjacent is, I did an example over here. These are simply angles that share one side. So BC is part of both of these. So if you look at the letters of the angles, ABC and CBD, they both have the letters B and C, which means that they must be adjacent. And so then here I write the converse. If two angles are adjacent, then they are a linear pair. And in the example I showed here, we can obviously see that angle ABD does not form 180 degrees, so it's not a linear pair. So this means that it's false, which means we cannot reverse it or write a biconditional. Looking at biconditional again. All right, so we're given this statement. So I'm using this as my hypothesis and my conclusion. I'm writing another biconditional. This one, just because the wording's a little different, so I had to kind of highlight it a little bit differently here, and we write this. Now we're looking at the first law of detachment. And so here's where we have a true statement here, and then we take away the parts and see if the parts are indeed true. And so we need this original conditional to be a true statement, and then if that hypothesis is true, the conclusion can be true. So let's look at an example of that. So if the robber is fast, then the police cannot catch him. So in this next statement here, it has to confirm that this is true or false. So if it said the robber is tall, that does not conclude this, so I have no conclusion. If it says the robber is a man, or the robber is a woman, or the robber is wearing a hat, or is wearing shoes. These things don't do anything to conclude this. So we just need these to match up. Once they match up, I can conclude the hypothesis. I'm sorry, the conclusion. And then we're looking at law of syllogism, and let's take a look at that. And so we have this kind of what's called chain reasoning. So we're looking at what we originally have: if P then Q, if Q then R, then P to R. So we see that both of these are sharing this Q here, this conclusion that was once a conclusion, then it becomes the hypothesis. And we need that to match in order for us to be able to come to this conclusion of P to R. So we see we want to come from P to R. We need this Q to match in the middle. So let's look at an example of that. So we've got, if Roger gets a new computer, then he'll give me his old one. If Roger gives me his old one. So we see we have a match here. So the conclusion here matches the hypothesis of the next statement, which means we can go from the original hypothesis, and then we can include that in our final conclusion. And so then we can write it here. If this didn't match, then we simply cannot write any of these conclusions. All right, so these must match here. And another example of this law, once again, we need this conclusion to match the other hypothesis, and we see that it does. I'll get a spanking, so we can go ahead and we can connect this original hypothesis to this conclusion. We can create this conditional. And then in the last one, we're combining both of these laws. So the first thing you want to focus on here is, what is the statement? So if the river is the longest in the solar system, then it is the longest in the galaxy. So we're given a fact about if the river in the solar system is more than 1,019 kilometers long. So we're given this, like, okay, if it's, then this is a basis for whether or not it's the longest in the solar system, which will conclude that it is the longest in the galaxy. So we're given that a certain river is 1,256 kilometers long. So that tells me that this is longer than this. And if it's longer than this, then that it satisfies this statement here, that if it's the longest in the river in the solar system, it's the longest in the galaxy. So if I know this information, that it is longer, then I can make this conclusion.